Whilst pointer-based and space-efficient, that is, they only consume space as and when changes are made to the source volume, clones are none of that. Clones are full, block-for-block copies of volumes, meaning that they're not space-efficient and they're not pointer-based. If we take our same source volume that we've been working with while explaining how snapshots work, and we assume that it's a 2 terabyte volume, then any clone that we make of this volume will be a full block-for-block copy of the source, and therefore also consume its own 2 terabytes of storage, meaning that our source and clone volumes use a combined total of 4 terabytes of storage, so zero space efficiency there. And a point we should probably have mentioned when we talked about snaps is that for both technologies, snaps and clones, we can have multiple copies, so multiple snaps and multiple clones of a single source volume. And as we might expect, this can quickly eat through space if these copies are clones, each clone consuming exactly the same amount of storage as its source volume. And obviously this won't be the case with multiple snapshots though, unless of course you have a massive rate of change against your source volumes. So, why bother with clones when they're not space efficient? Well, clones do have several positives. First of all, clones are fully independent of their source volumes. They can be sat on separate disks and separate disk pools. All of this meaning that if the source volume fails, any clones of it don't need to be affected by the failure. Whereas if we're talking about snapshots, then a failure of the source volume will also cause a failure of the snapshot, because any pointers in the snapshot will be referring back to a failed source volume. So clones are more resilient than snapshots. And because clones aren't based on pointers, there's no redirection operations going on inside of the array. A read to a block in the clone is always satisfied by the contents of a block in the clone, and the system never has to redirect the read back to the source volume, and this can give better performance. Also on the performance front, because no read requests have to be directed to the source volume, any work targeted at the clone has no impact on the source volume, whereas snapshots refer a lot of read requests back to the source volume, meaning that the source volume has extra work to do. But let's not forget, this full independence, with its associated higher performance, lower impact on the source volume, and greater resilience, all come at a cost. Clones consume large amounts of capacity. Now, one final point on clones. Just like snapshots, clones can also be instantly available, despite the fact that they're full block-for-block copies of a source volume. Now obviously, it's not possible, for example, to make an instant block-for-block copy of a 2 terabyte volume. Copying 2 terabytes of data takes time, no matter how good your storage array is. So what usually happens, in order to make clones instantly available, is that when initially created, the clone is actually a pointer-based snapshot. Only in the background, the system starts making the full copy, so that after a short or a shortish period of time, the full block-for-block copy is eventually made, and it's no longer a pointer-based snapshot. So, that should have us all covered off on how snapshots and clones tend to work. Now, snaps and clones can be either array-based or host and hypervisor-based. Generally speaking though, the way they work is the same, with the major differences usually being around performance and scalability. Let's have a look at array-based snapshots and clones.